Okay, so today's speaker will be Ziquan Zhuang from MIT, and he will give the second lecture of the lecture series of Introduction to K-stability.
All right, so thanks, Chenyang, for the introduction, and thanks for having me here. It's a great pleasure to speak. So today I will continue with the lecture on K-stability. So on Tuesday, we can basically introduce the definition of K-stability and also explain some ways to understand the definition using objects that we are more familiar with in birational geometry, such as divisors on birational models and complements. Okay, so today I want to switch the gears a little bit. So I want to introduce a few, some of the major conjectures in this area and try to explain why they are related to each other. And then next week, we'll probably see some ideas that goes into the proofs. So the first conjecture I want to start with is the so-called Donaldson conjecture. And this is one of the main reasons that K-stability was introduced. So the conjecture basically says the following. It says that if I have a Fano variety X, which might be singular, so this is a possibly singular Fano variety, then the conjecture says that so X has so-called Kähler-Einstein metric. So a Kähler metric with constant Ritchie curvature. So such a metric exists if and only if the Fano variety is so-called K polystable. So on the left-hand side, a Kähler-Einstein metric is certainly a differential geometric object, while on the right-hand side, as we have seen on Tuesday, K polystability or K-stability in general has a purely algebraic definition. So this is a statement that relates differential geometry and algebraic geometry. So this conjecture was already known in some cases. For instance, so one of the direction going from the metric to stability was already known by Berman in full generality. Any singularities is fine. The backwards direction is harder, but at least when the Fano variety is smooth, that was already proven a while ago by Donaldson Conjecture and Tian using so-called continuity method. Okay, so at least today we are going to focus on the singular case of this conjecture. And since the statement here involves the differential geometric side, it doesn't make sense if I skip the differential geometry there. Okay, so let's start from there. So if we want to construct a Kähler-Einstein metric on a singular Fano variety, the analytic method that's involved is the so-called variational method. So let's first recall that so when I say Kähler-Einstein metric, it's a Kähler metric whose Ritchie curvature is proportional to the metric tensor. But since I have a Fano variety, I can always rescale so that the constant here is 1. And because I have a Kähler metric, usually it's more convenient to replace the metric by the corresponding Kähler form. Okay, so I get this equation. Now, on the Fano variety, so in general, the Ritchie curvature is going to represent the first Chern class of the variety. So it becomes very natural to look at the following space of so-called Kähler potentials. Kähler potential, so which is roughly, you can write equal, but maybe I should just write approximately, it's roughly this space. Okay, so let me just write equal because the technical details is not so important for us. Okay, so then it's very natural to look at the Kähler forms that represent the first Chern class. Right, so if you want to find a Kähler-Einstein metric, you look at this space and find one that satisfies this Einstein equation. Okay, so I guess perhaps Mabuchi is one of the first person to study Kähler-Einstein metric using variational method. So he did the following. So first, he introduced an energy function on this infinite dimensional space of Kähler potentials. So he called this the K energy. And this is nowadays also called Mabuchi's K energy. So this is just a function on this infinite dimensional space. And what's important is that the critical points of this energy function are exactly the Kähler-Einstein matrix. So in other words, if you write down what the critical points, the conditions for being critical, that's exactly this equation. Okay, so he also introduced a metric, a natural metric on this infinite dimensional space, and he showed that this energy function is convex along the geodesics under this metric. Okay, so that's the analytic input. Now, what do we know about a convex function and the critical points of that? Well, so here is a typical picture of a convex function that has critical points. And here is another typical picture of a convex function that doesn't have critical points. So the difference is that in the first picture, if you look at the slope at infinity, it's positive. While in the second one, in the second picture, the slope at infinity is non-positive. Okay, so if in the end, your goal is to construct critical points of this energy function so that you get Kähler-Einstein metric, you'd better ensure, or at least you should probably try to show that when you look at the slope at infinity along geodesics for this energy function, you get something positive. Now the issue is in general, it's not so easy to write down geodesics because the metric is abstractly given. On the other hand, it's easier to write down some kind of like algebraic rays in this infinite dimensional space, although they are not geodesics. And that exactly comes from the test figurations. Okay, so you can actually think of a test figuration as some kind of algebraic rays in this space of Kähler potentials. So how is that possible? So let me first recall that so a test figuration consists of a family over the affine line together with the GM action, such that if you remove the central fiber, like if you remove the origin, then the fiber over this the puncture affine line are just the given Fano variety X. Okay, so another convenient way to think about this data is to start with some embedding of the Fano variety in some projective space using the pluri anti-canonical line bundle. And then you choose a GM action on this ambient projective space. Then as you take the Hilbert scheme limit, you get this test figuration. Now, if I twist this embedding that I start with, using the GM action, I get a family of embeddings into the same projective space. Okay, so the parameter sits in C star. And so I can look at the pullback of the Fubini-Studi form, the standard Fubini-Studi form on the projective space 2x using this family of embeddings. So I get a family of Kähler forms. And up to a certain factor, they represent the first Chen class, so they live in this space of Kähler potentials. Okay, so I can just write they live in H up to scaling. Okay, so in the end, I get basically a curve in the an algebraic ray in the space of Kähler potentials. This is theory, not geodesics, but it still makes sense to look at the slope at infinity for this rays. So so Ding and Tian computed this number, and they found that if you look at the slope at infinity of the Mabuchi energy function along this rays, what you get is exactly the Futaki invariant of this test figuration. Okay, so now let's recall that K-stability or K-polystability requires that this test figuration, the Futaki invariant of test figurations are almost always positive. So so then the strategy is more or less more clear now. So assuming that this Futaki is almost always positive, you want to hope that this algebraic rays that comes from test figurations, they approximate geodesics in this space of Kähler potentials really well, so that they also give you positivity of the slope of this energy function at infinity along GLSX. Okay, so that's roughly the idea from the differential geometry side. So of course, this approach has been developed in the past many years, and it was finally achieved maybe 2 years ago, last year, something like that, by Berman, Buxom, Johnson, Tian Wang, and Shi. That the following statement holds. So basically, they say that if you just assume a little bit more positivity about the Futaki invariant, then you do get Kähler-Einstein metric. And so here's the precise statement. So they show that X has the Fano variety has a Kähler-Einstein metric, if and only if the Fano variety is so-called reduced, uniformly K-stable. Reduced, uniformly K-stable. Okay, so this is again has an algebraic definition. It's slightly more technical, so I only define this in a special case when the automorphism group is finite. Okay, so when the automorphism group is finite, what they show is that the existence of Kähler-Einstein metric is equivalent to saying that the Fano variety is uniformly K-stable. So in some sense, this reduced part takes care of the automorphism. Okay, but I'm not going to go into that today. Okay, so so then maybe I should at least define what's uniformly K-stable. But are there any questions up to this point?
Sorry, do you assume smoothness in this result?
No, so any X.
Okay.
Any Fano. Yeah. So I guess so originally, so Berman, Buxom, Johnson, they proved it in the smooth case, but then it was later realized that you can also do it for a singular case. Yeah. Okay. Any other questions? All right, so then let me define this uniform stability. So let me first recall that, so we say that the Fano variety is K semi-stable. So I'm going to define things using the Relative Criterion of Fujita-Lee. So last time we mentioned that, so on Tuesday, I guess, we mentioned that the Fano variety is K semi-stable if the so-called log discrepancy function is greater than or equal to the expected vanishing order for any divisor E over X. So for any divisor on some birational model of the Fano variety. And it's called K-stable if and only if this inequality is strict. Okay, so it's always greater than or equal. So now I'm going to say that X is uniformly K-stable if there exists some number epsilon positive such that so the log discrepancy is greater than or equal to 1 plus epsilon times the expected vanishing order. Okay, so so maybe an equivalent way to phrase this is to use the delta invariant. So let me recall that the delta invariant or the stability threshold of a Fano variety is defined as the infimum. There are several ways to define it, but one of them is to define as the infimum of A over S, so log discrepancy over the S invariant, where the infimum is taken over all divisors on birational models of X, so all divisors over the Fano. Okay, so so the equivalent definition is that the X is called uniformly K-stable if this infimum is greater than 1. Okay, so K-stable says that all these individual ratios are greater than 1, while uniform says that if you take the infimum, it's also greater than 1. So apparently the uniform version is looks stronger than the usual version. And so now combined with this statement, you see that so the original Yao-Tian Donaldson conjecture that Kähler-Einstein metric is equivalent to polystability is essentially reduced to saying that this reduced uniformly stability is the same as the usual polystability, or this uniform K-stability is equivalent to the usual K-stability. Okay, so that's one of the results that we show with in the joint work with Yuchen and Chenyang. Okay, so the statement is that so K polystability is equivalent to this reduced uniformly K-stability. Maybe I'll just abbreviate things like this. Okay, so UKS is uniformly K-stable. Well, so being K-stable is equivalent to saying that so it's uniformly K-stable. Okay, so it turns out in the end that they are equivalent. So in particular, this will prove the Yelkin and Donaldson conjecture combined with this analytic result. All right, so so this last statement, this so K-stable is equivalent to uniformly K-stable, is actually a special case of something called the the optimal destabilization conjecture. And so that also has some very close relation with the K-moduli conjecture that I'm going to introduce next. Okay, so I'm going to come back to this statement afterwards, but let me now switch the topic a little bit and introduce the K-moduli. Okay, so are there questions so far? All right, so okay, so now let me introduce the K-moduli. So the K-moduli is basically it's basically an attempt to construct a compact moduli space of Fano varieties. And so it's already well known that if you want to construct a moduli space of Fano varieties, you have to impose some stability condition, because otherwise it's not going to be separated. So so for instance, you might have like, so P1 cross P1 degenerating to, so this is the smooth quadratic surface, you can degenerate to the singular quadratic surface. So everything here has quotient singularity. It's an isotrivial degeneration, meaning that if you take everything into the moduli space, so then this point, the moduli point for this variety will contain the moduli point of this singular one in the closure. So we don't have a separated space. Okay, so this K moduli is an attempt to construct a separated and in the end projective moduli space of K, so maybe in this sense I should write K polystable Fano varieties. Okay, so this was previously conjectured, but as I try to explain, we will try to explain in this lecture series. This is now, the construction is now done. Okay, so so I guess this K moduli was conjectured to exist maybe a decade ago, and a lot of work has gone into the study of this topic in the past 10 years. So let me try to first summarize what was already known. Okay, so it's due to this many authors, and let me try to summarize it in 4 different parts. Okay, so in order to construct this moduli space, let me first fix some numerical invariant. So I'm going to fix an integer, which basically represent the dimension. And I'm also going to fix a rational number, which basically represent the n-canonical volume of the Fano variety. Okay, so the first part of this statement concerns the moduli stack of K semi-stable objects. Okay, so let's consider this moduli functor. So the notation here is here. So the upper script stands for K semi-stable. The lower scripts are just the numerical conditions that I fixed. Okay, so this functor sends every scheme over. So I write the field of complex number. You can do any algebraically closed field of characteristic 0. Okay, so it sends a scheme to the group point of flat projective families over my chosen scheme. So it's a family of K semi-stable Fano varieties of the given dimension and given anti-canonical volume. With an additional condition that the family should satisfy the so-called Kähler condition. Okay, so this Kähler condition is not so relevant in this talk. It's more relevant when the base scheme is non-reduced. So at least for most of the purpose, like when the base is normal, you can just assume. So this condition basically just says that the relative canonical divisor is Q Cartier. Okay, so this is the moduli functor that we consider. So the first part of the theorem of the statement says that this moduli functor is represented by an arting stack of finite type. So maybe more concrete, in the more concrete fashion, this means that, so first, so K semi-stable Fano varieties of this given numerical condition are bounded. So that was proved by Chenyang. And also another different proof was given by Chenyang and myself. The second part of this statement is that, so as you look at this bounded family of Fano varieties under this condition, being K semi-stable is an open condition in the family. Okay, so that was proved by Xu and also by Harold, so Bloom Liu Xu using different arguments. Okay, so that's basically the content of the first part. All right, so now we have a K moduli stack. So the second part of the theorem concerns the corresponding moduli space. Okay, so the good moduli space of this stack. Okay, so it says that there's K moduli stack admits a good moduli space, and in fact a separated good moduli space. And in fact, the close points of this good moduli space are in one-to-one correspondence with the polystable objects. Okay, so I can just write, so this moduli space parameterizes K polystable Fano varieties of the same dimension and volume. Okay, so maybe this is the first. If this is the first time you see this good moduli space, so let me just spell out what this means. So more concretely, this means that so there is a map from my stack of semi-stable objects to an algebraic space. So let me also give a name to this space since I'm going to use it in the other statements. Okay, so it's MK polystable and the numerical condition. Okay, so let me finish this statement. So the stack has a map to an algebraic space. Okay, so this is an algebraic space such that a tile locally on this algebraic space downstairs. So a tile locally, this map just looks like the map from a quotient stack, so a fine modular reductive to the corresponding GIT quotient. Okay, so that's what the statement means. And moreover, this algebraic space is separated. So I guess the separated part was proved by Bloom and Xu, while the existence of good moduli space was proved by so Alper, Bloom, Halpern-Leitner, and Xu in a different paper. Okay, so right, so now we have a moduli space of K polystable objects, which is separated. So the remaining part of the question is whether it's proper and projective. Okay, so the third part of the statement concerns the properness. So it says that this good moduli space and K polystable is proper if you assume the so-called optimal destabilization conjecture. Okay, so this is proper if the so-called optimal destabilization conjecture holds. Okay, so I'll explain this afterwards. So let me first finish the entire statement. So finally, you also need to say something about the projectivity. So okay, so I guess what was originally proved in the paper, in the joint work with Chenyang, is that so every proper subspace of this moduli space, K polystable, is projective. Essentially, if K polystable is equivalent to uniformly uniformly stable. So in other words, if the Tian-Donaldson conjecture holds. Right, so in the end, if you have the Tian-Donaldson conjecture and this optimal destabilization conjecture, then you get everything you want to know, like properness, projectivity about this modular space of Fano, K semi-stable Fano varieties. Okay, so that's the entire statement. Okay, is everything okay so far? So in this talk, I'm going to focus on the third part, which is the properness. So let me first tell you what is this optimal destabilization conjecture. All right, so here's what it says. So it says that if I have a Fano variety that's not uniformly K-stable, so in other words, the delta invariant is at most 1. So again, let me remind you. So delta is the infimum of this A over S. So assume that this is less than or equal to 1. So in other words, the Fano variety is not uniformly K-stable. Then the conjecture is that this infimum that defines delta is in fact a minimum. Okay, so then this delta invariant is actually equal to some A over S, some log discrepancy over S invariant for some divisor E over the Fano variety. Okay, so this is in general false if the delta, if it's uniformly K-stable. Okay, so the conjecture is that it's true when it's not uniformly K-stable. Okay, so let me first remark that yes.
Is there a counterexample if delta bigger than 1?
So in my joint work with Hamid, we have this cubic surface. So I guess, okay, so for Fano, we don't have an example, but if you put boundary there, then you do. So I think there, if you just take that line plus conic and increase the coefficient to very close to 1, then all the minimizers will be there, will be at that center. And there we already showed that it's not, delta is irrational there, so it's not computed by a divisor.
So for log Fano pair is false.
Yeah, so for log Fano pair is false. Yes.
Okay, thanks.
Okay, so are there other questions? No. Okay, so all right. So let me first remark that so this optimal destabilization conjecture already contains this equivalence of K-stable and uniformly K-stable as a special case. Because so let me write that down. So the remark is that so this optimal destabilization conjecture implies that being K-stable is equivalent to being uniformly K-stable. I mean, after all, if you so K-stable says that all these ratios are greater than 1, while uniform says that the infimum is greater than 1. But if the infimum is the same as minimum, then they are the same. Okay, so in particular, either if you are interested in the Donaldson conjecture, or if you are interested in the properness or projectivity of the K-moduli space, this is the main algebraic statement that we should focus on. Okay, so before we talk about that, so let me first try to explain why the properness, maybe very briefly, why the properness follows from this optimal destabilization conjecture. So I guess maybe the first thing I should remark is that so associated to this divisor that computes the delta invariant, there is also an optimal degeneration in some sense. So that was a result of Blum, Liu, and Zhou. So they show that if this delta invariant is computed by some divisor, like this, and the Fano variety is not uniformly K-stable, meaning that delta is at most 1, then you can use the so-called risk construction to get a special test configuration of your Fano variety. So then this divisor E is going to induce a special degeneration. From the original Fano variety to a different Fano variety. So basically this means there is a special test configuration such that the general fiber is the original Fano and the special fiber is something else. Maybe the same, but something. Okay, some other KLT Fano variety. And what's crucial here is that in this degeneration, the delta invariant is preserved. That's that. So the delta invariant of the original Fano is the same as the delta invariant of the central fiber. And since this is comes from a test generation, the central fiber now has a GM action. Okay, so it's quite frequently not the same as the original one. Okay, so we have this quite special degeneration. And why is this useful for us? So now let's say we want to prove the moduli space of K polystable objects are proper. Then apparently we are going to use the Relative Criterion of properness. Oh, so maybe I forgot to say so. So this third part is due to so Blum, Kähler-Einstein, Liu and Xu, which is based on an earlier criterion on the properness of good moduli space that was developed by Alper, Kähler-Einstein, and Heinroth. Right. So now so let's say we want to prove properness, then so we apply the relative criterion, and that means for any family of K semi-stable Fano varieties over a puncture curve, we want to construct an extension of this family over the puncture. So we want to show that they exist. I can compactify this family over the puncture such that the central fiber of the compactified family is also K semi-stable. Right. So then they will prove the properness. Now, this is the question mark. So in general, at least a priori, what you can construct using minimal model program is an extension of this family so that the central fiber remains Fano and KLT. Okay, so at least in general, what you can say is that the central fiber is Q Fano. Okay, so that's what you can always do. And then the goal is it K semi-stable? All right, so then suppose that it's not, then the idea is maybe you can replace this family by something better and show that the symmetrical fiber the stability of the central fiber improves. Okay, so you might want to, so if the central fiber here is not semi-stable, then what you want is maybe a new family, probably up to a base range of the base curve, such that the stability of the central fiber, well, so maybe improves. So maybe a new family with better stability. Okay, so that would be the ideal situation. So in fact, basically what they show is that if you assume the optimal destabilization conjecture, then such a new family always exists. So so roughly you can actually describe the central fiber of this new family in some sense. So the central fiber of this new family comes from, so you first take, so the original central fiber, which is not semi-stable. Now the optimal destabilization conjecture says that we have a special degeneration to something else. Okay, so this is the optimal destabilization. Okay, so we get to something else. And then basically in the new family, the central fiber is obtained by deforming this one. Okay, and then you somehow deform this to get a new object. Now, because in the first specialization process, the delta invariant is preserved. Well, this delta invariant is basically a log canonical threshold. So when you deform it, it's usually going to increase. So when you deform it, you get something, a new field-in whose delta invariant is usually at least not smaller than this. And actually what they show is that after finitely many steps, it gets bigger. Okay, so if you continue this process finitely many times, eventually you get something that's K-semi-stable. Okay, so maybe this still seems like a black box. So I guess a rough picture is roughly like this. Okay, so here I have my base curve, and so I'm picturing everything in a suitable Hilbert scheme, right? So if you want to take limits, you take limits in Hilbert scheme. So so started from the original family of semi-stable Fano varieties, I can look at the corresponding, so I embed this family in some projective space, for instance, and I can look at the corresponding maybe PGL orbits in the Hilbert scheme. Okay, so maybe on my generic points of the curve, I get some orbits in the Hilbert scheme of the Fano varieties in my chosen family. Now, if I want to compactify this family, I'm going to specialize these orbits to the central fiber. Now, as you specialize, the orbits break up into several orbits corresponding to different choices of field-in. And at least I know that because I already have a field-in, at least I know that one of the orbits come from the PGL orbits of my chosen field-in. Okay. However, there could be other orbits, right? So the optimal destabilization conjecture basically allows us to go from your starting orbits and use the degeneration to go to the boundary, and then you deform to get to a new orbit. And in this process, the delta invariant keeps non-decreasing, and after finitely many steps, you actually get to something that you want, which is K-semi-stable. So that's roughly the idea. And of course, I'm skipping a lot of technical details. Okay, so in the end, the upshot is that the properties of the K-moduli space also follows from this optimal destabilization conjecture.
So you also use delta is ACC or finite many values, right?
Yeah, I see a lot of details, of course. So yeah, so I guess when you start with some lower bound of the delta invariant, then you get a bounded family, and in the bounded family, the delta invariant takes only finitely many values, which is the constructability that you prove with Chenyang and Harold. All right, so I think so far I've reduced everything to the optimal destabilization conjecture. Why do I keep failing to speak this, pronounce this word? Okay, so, and that was exactly one of the main theorem that we proved. So in the joint work with Chen and Chenyang, that so this optimal destabilization conjecture holds for any Fano variety, so including the singular ones. So of course, for smooth ones, this was already known using analytic methods. All right, so so I guess in the remaining parts of this talk and also in the 2 lectures next week, we'll try to give some ideas about what's going on behind such a statement. Okay, so so but at least naively, there is not much we can do to start with. So the conjecture says that so I have an infimum which is a minimum. So the first idea maybe, so now let's take a sequence of dividers over the Fano variety that approximate this infimum, and let's see what we can do. For instance, can we take the limit in some sense? Okay, so in any case, let's choose a sequence EI. So these are divisors over the Fano variety such that the corresponding log discrepancy over the expected vanishing order approximate my delta invariant. Okay, so then you want to ask, is there a way to take the limits of this sequence and get a new divisor somehow? So that's in general hard because these divisors, they live on various birational models. So you can go to higher and higher blowups, and there is no sensible way to take limits as divisors on the variety. However, there's a way to take limits as valuations. So each divisor here is going to give me a valuation, a divisorial valuation actually, just by looking at the vanishing order along these divisors. Okay, so this gives me a valuation on the function field of my Fano variety. And now you might wonder, can we take a limit as valuations? And especially since, so first, there is a weak topology on this valuation space. So it always makes sense to take limit in this sense, in this topology. And also my log discrepancy function and my expected vanishing order both have a natural extension to the valuation space. So they extend to the space of valuations on the variety. So you can just take the limit of these valuations if you want. Okay, so this seems to be quite promising. The only problem is that, so if you take the limit in this case, in this sense, most of the time you get the trivial valuation. You can imagine, so if you take, you start with P1 and you take a bunch of points on P1, then so the limit valuation will have a center, but if these points, they jump around, then the limit valuation, the only sensible center is the generic point. So then you get the trivial valuation. So so that means if you want to take a limit valuation in this way, you have to be clever. So such a process is actually possible, and that was shown by Xu and Blum Liu Xu. So the point is that these valuations, they are not entirely arbitrary. So on Tuesday, Chen already explained that these valuations, they can be actually chosen as log canonical places of bounded complements. So they can be chosen as log LC places of bounded complements. So so if you combine this with the invariance of plurigeneral, so that allows them to show that this delta invariant is actually computed by some valuation. So you can take this limit in some sense. Okay, so they show that this delta invariant, since I want the complements part, so let me write. So if the delta invariant is at most 1, then so then this delta invariant is equal to the log discrepancy over the expected vanishing order for some valuation that's also an LC place of complements. So the limiting valuation is also not arbitrary. For some variation V, that's also an LC place of complements. Okay, so essentially what happens here is so only what you might worry about getting the trivial valuation is because the center of these valuations, they jump around. But since now they are LC places of a bounded complements, there are only finitely many families of these complements. And invariance of plural genera in some sense guarantees that if you move these valuations in the same family, then this A over S, they don't change. So you might just start by moving everything to the same center and take the limit over there. So that's based in some sense roughly what they achieve. Okay, so in the end, we get a valuation that computes this delta invariant, and what's missing, if you are aiming for the optimal destabilization conjecture, is that we need this valuation to be divisorial. So they come from the vanishing order along some divisor on some birational model, or at least proportional to that. Okay, so the only missing part is that we want V to be divisorial. In other words, it's proportional to the vanishing order of some divisor. Okay, so but in any case, if you go back to the way we use the optimal destabilization conjecture, what we are more interested in is this degeneration. Okay, so now you might ask yourself, so although this minimizing valuation V may not be divisorial, maybe there's still a way to write down the degeneration. So in fact, that's possible. So in the case when V is divisorial, the degeneration here can be actually written down quite explicitly. So it already follows from the construction there that so if this the minimizing valuation is divisorial, then we can actually write down what's the central fiber of the degeneration. So so it's given as the approach of this graded algebra, where R is the anti-canonical section ring of my Fano variety. Okay, so for integers, and so V is my valuation. So that induces a natural filtration on this ring. So V induces a filtration F on the space of sections, where so F lambda is given by the sections whose value is at least lambda. Then you take the graded quotients to construct this graded algebra. So this graded algebra is defined as, so you take the direct sum of all mn lambda of the graded quotients of this filtration. Or if you want more concretely, this is just the direct sum of all mn lambda of f lambda modulo f greater than lambda. So the sections whose vanishing order is greater than that number. Okay, so this is what you get using the so-called risk construction. So the upshot is that so when the minimizing valuation for the delta invariant is divisorial, we actually get this approach as the central fiber. So now we get a valuation that's not necessarily divisorial, but most of these constructions still make sense, right? So we have this any-canonical section ring. I take a valuation that gives me a filtration of these sections. So I can write down this graded approach, graded algebra, and take the approach. So the only issue is that if I want to take the approach of something and get a variety, I'd better assume that this graded algebra is finitely generated. Okay, so that motivates this so-called higher rank finite generation conjecture. Okay, so it says that so actually for any evaluation, all right, so I should first write, so if the delta invariant is at most 1, so meaning that the Fano variety is not uniformly K-stable, then it is the conjecture is that any evaluation that computes this, actually maybe I can just write, so if the delta invariant is computed by some valuation, and it's at most 1, okay, then this graded algebra that I wrote down earlier is finitely generated. Okay, so that's the statement. So again, so what we show in the recent work together with Chen and Chenyang is that so this higher rank finite generation conjecture holds. Okay, so that's the statement. Let me see. Yes. Okay, so right. So, are there any questions up to this point?
So if I understand correctly, the kind of order of the proof is that you first show the HRFG conjecture, and from that you recover that in fact this valuation is divisorial.
Yes. Yes.
Mm-hmm. Thanks.
So probably this will be clearer next week when you talk about the proof, but is it possible to say one word? I mean, what's the role of these conditions that delta is less or equal than 1?
So actually it's already here. So in general, this valuation can be more arbitrary, but when delta is at most 1, then all the minimizing valuations, they come from log canonical places of complements. In general, that's not true. So in general, we know the variation is quasi-monomial, but it's a little bit harder to give a criterion for the finite generation without the complements. All right, so let me see. I have 6 minutes. Let me decide if I want to go over some parts of the. Right, so let me just so since I still have some time, so let me just say very quickly a few words why. So since Jakub already asked that, so let me just quickly remark why the higher rank finite generation implies the optimal destabilization conjecture. Okay, and then next week we can mainly focus on the finite generation without worrying about the rest. Okay, so so the key point is that so first, this minimizing valuation, they are not arbitrary, as I just mentioned when I answer Merchant's question. So in fact, what they show is that when the delta invariant is at most 1, then any minimizing valuation of the delta invariant is an LC place of complements. And in particular, these valuations, they are quasi-monomial. Okay, so the first fact is that this minimizing valuation, this valuation V, is quasi-monomial. So what that means is that you can find a log resolution together with a simple normal crossing divisor over the Fano variety, such that and okay, so in some weights so these are positive, such that, so basically so if I write down this, if I write this simple normal crossing near their center as this, so the local equations are x1 through xr, then my valuation is basically given by so the value of xi is my chosen weights, and then you just take the minimal extension of this valuation, of this as the valuation. So in some sense, you are taking the weighted blowup at the intersection of these divisors with weights of alpha 1 through alpha, if these numbers are rational. Okay. But in general, so if the numbers are rational, you get the divisor, but in general, you only get such a quasi-monomial valuation. So basically, so since the valuation is an algebraic place of complements, what you do is, so you take that complements, you resolve it, and then so you get some exceptional divisors of coefficient 1. So that's where the log canonical places come from. So you can take all kinds of weighted blobs along those divisors. But you can take irrational weights, and that gives you a quasi-monomial valuation in this sense. Okay, so that's the first part, first point. Now, now once you have this, you might guess, you might make a guess, right? So, so what are the candidates for the minimizing divisor in the optimal destabilization conjecture? So then you might just perturb the weights to rational numbers. Okay, so that's in fact the case. So and this follows from a proposition that was proved by Chenyang and by also I think by Shi and Chenyang. So basically what they show is that so if you assume okay, so let me give some notations here. So so now using this stratum, I can write down many different other quasi-monomial valuations using different weights. So basically, for any data, so if I choose a different weight, I can also write down the corresponding quasi-monomial valuation. So the corresponding quasi-monomial valuation. So now what they show is that, so assuming this weighted algebra for the minimizing valuation is finitely generated, then and so you can actually achieve so that this weights alpha, they are Q linearly independent. Then the S invariant. So if you look at the S invariant, you get actually a linear function in the neighborhood of the original weights. So this function that sends the weights to the S invariant of the corresponding quasi-monomial valuation is linear around the starting weights. Okay, so maybe I'll explain this next time, or at least partly explain this next time. But at least this will imply the optimal destabilization conjecture, because you see, so the log discrepancy function is linear with respect to the weights, while the expected vanishing order is now also linear with respect to the weights. So if you have two hyperplanes, one is always greater than the other, but they are equal at some point, then they are equal everywhere. So you can always perturb the weight to something rational, and get a divisorial valuation that also minimizes this A of S. And that gives you the divisor you want in the optimal destabilization conjecture. All right, so I'll probably leave things here and then I'll continue next Tuesday.
Okay, so let's first thank Ziquan. So any other question? Okay, it seems people are fine. So then let's thank Ziquan again. And
So
And,
stop share.
we will continue our summer school next week, next Monday.